Okay, continuing where we left off last time here in 10.7, we need to write out some theorems. So now that we have this idea that we can take a power series and we can convert it to a function, there's a lot of theorems that are going to come into play, and I'm going to show you some steps on how to answer the homework questions. So the first theorem, this is called the convergence theorem of a power series. And what it says, if a power series, and when we're talking about a power series, just to write it out, this is going to be our sum in going from 0 to infinity. Remember, we're going to have those constants out in front, and then our x to the end. Okay. If a power series converges at x is equal to c, so this is not the same coefficients as being out in front here. This is going to be an x value c that this thing converges to. As long as this x equals c is not 0, I'll put this in parentheses here, then it converges absolutely for all absolute value x less than the absolute value of c. If the series diverges at some point x equals d, so just some other value, then it diverges for all absolute value x is less than absolute value d. Alright, so what this theorem is saying is that if you can figure out somewhere where it converges, then it is always going to converge less than that number as far as absolute value goes. If you found somewhere where it diverges, then it's always going to diverge for any number beyond that value. So just to kind of show you exactly what this means, if you look at a number line, sorry, it's an awful color there. So if you look at some number line where you have 0, remember that this is a power series centered at 0, so we're not centering this at anywhere else, but it's going to hold for when you do center it somewhere else. We'll see that in the next theorem. So if it is centered at 0, if you find some value c, and you know it converges there, you automatically get that it converges at all values between c and negative c. So this would be where it converges. If you find some place d where you know it diverges, then you automatically get that it diverges everywhere above d and everywhere below negative d. The point of that is that when you have convergence of a power series, it's only going to converge close to where you are centered. So here it's going to converge close to 0. Anything far away makes it harder and harder for it to converge. All right, let's look at the next theorem. This is actually a corollary onto the last theorem. The convergence of a series, so this is just a generic series. This one does not have to be centered at 0. Let's look at one that's now centered at a. So the convergence of this series is described by one of the following. And there's 3 different things here. The first way is that there is a positive number r such that the series diverges for x with absolute value x minus a is greater than r, but converges absolutely for x with the other way around. Absolute value x minus a is less than r. The series may or may not converge at the endpoint. Alright, so this is basically saying what I was showing you up here. So just another quick little number line. So what this first one is saying is that now if we're centering it at a, so we're no longer centering at 0, or a may be 0. If I can figure out some number r What this is saying is that if I bound my A between R, this is really A plus R here, sorry. This would be A minus R. So if I go R to the right and R to the left of A, my series converges in this interval. Anywhere beyond that A plus R and A minus R, my series diverges. So the first possibility for one of our series is that we get this interval of convergence, where I go up R and down R from the center. Okay. So I can just go away. Great. The second thing, it's possible that your series converges absolutely for every x. Another way of thinking about this is you could think of it as that your R value is infinity. So this R is going to have a name to it here in a minute. It's called the radius of convergence. This is just saying that the radius of convergence is infinity, and it doesn't diverge anywhere. It converges absolutely on the entire number line. The other possibility, the opposite of this, is that the series diverges everywhere except at x equals a. You are always going to have convergence at x equals a, because x equals a is just going to give you 1 over and over and over again. Not 1, sorry, 0. I don't know what I was thinking. 0 over and over and over again. All right, these are the only possibilities. So it is possible that you have this interval of convergence. It's possible that your convergence is the entire number line. It's possible that your series diverges everywhere, and that is it. From this, we're going to have some definitions. So the first thing is that R value that we're talking about. This is called the radius of convergence. The other thing is the interval. So same definition here, but the interval centered at A with radius R is called the interval of convergence. Okay. This is finally going to lead us into your homework questions and potentially test questions in the future here. So what we're looking at is we're going to be looking at steps to test a power series for convergence. All right, and 3 different steps here. The first thing that you want to do is you're going to use the ratio test or potentially the root test, whichever one looks easier for you to find the interval. This interval that we're talking about, this is the absolute value x minus a is less than r interval. The second thing that you want to do here is that if the interval of convergence that you found in the first part, this is the interval of absolute convergence, is finite. In other words, the R value that we found here is not infinity. Then you want to test for convergence at the endpoint. All right, once you've tested both of the endpoints, you're ready to write it all out. And then the third possibility, if the interval of absolute convergence is that finite interval, so a minus r is less than x is less than a plus r, then that means that we have divergence everywhere else. So we're going to have divergence for absolute value x minus a is greater than r. So beyond that value on that number line I drew a little bit ago. All right, let's look at some examples of this. These are pretty much exactly how your homework questions are going to look. All right, for what values of x does the power series converge? This is our power series here. So the sum of -1 to the n minus 1 of x to the n divided by n. I don't like the way that wrote that. Well, okay. So we're looking at this. -1 to the n minus 1, x to the n divided by n, as n goes from 0 to infinity. So this is my power series. This is not geometric anymore, so we can't use the geometric series here. We're going to have to use either the ratio test or the root test. Both of them would be equally as easy. I'm just going to go ahead and do the ratio test just so we can get some more practice with that. So we're going to use the ratio test. Remember that the ratio test is that we want to look at the limit as n goes to infinity of that weird absolute value. It's the absolute value of the n plus 1 term divided by the absolute value of the nth term. So for us, this is going to be the limit and then just writing in the n plus 1 term here, we're going to have my numerator will end up being -1 to just the n times x to the n plus 1 divided by n plus 1. Okay. And now that's going to be divided by the nth term, which is just -1 to the n, and then that x to the n divided by n. There you go, looks nice. Okay. My -1, oh sorry, this should have been a -1 power here. The -1 to the n and the -1 to the n minus 1, they aren't going to do anything because of the absolute value. So we can just drop those. We also want to look at what happens with this. So I'm going to rewrite this a little bit by taking the first top fraction and dividing it by or multiplying it by the reciprocal of the denominator. All right, so we still have our limit at n goes to infinity. I'm going to leave the absolute value because we haven't dropped that yet. We're just dropping the -1 from the absolute value. And that's going to be my first fraction here, the x to the n plus 1 divided by n plus 1. That multiplied by the reciprocal of the denominator fraction n over x to the n. Okay. I'm going to rewrite x to the n plus 1 as x to the n times x. So let me just copy paste this over and show you what that's going to look like. So this x to the n plus 1, I'm just going to use the product rule for exponents here and write that as x to the n times x. Now my x to the n on top and bottom cancels out, and we're left with this. So we're just going to have an x up top there. This x to the n and the denominator down here is canceled out just to be a 1. Okay, so we can rewrite this. Still having the limit as n goes to infinity, still have the absolute value. And now it's going to be x times n up top in the numerator divided by n plus 1 in the denominator. Sorry, there should be an n plus 1 down here, not an x plus 1. As my n goes to infinity, my numerator goes to infinity, my denominator goes to infinity, so I get infinity over infinity. That's going to be L'Hopital's rule. Remember with L'Hopital's rule, we're going to take the derivative of the top and bottom separately. So we're still looking at the limit as n goes to infinity. Still have the absolute value. My numerator's derivative with respect to n is just x. My denominator derivative with respect to n is 1. Okay. Remember that x is a constant as far as n is concerned. So if this is all that I have left over, now if I take the limit as n goes to infinity, it just approaches the absolute value of x. I know this is a long process, and I did it slowly, but this will go a lot quicker the more practice that you get. We just use the ratio test, and remember that this number that we get in the end, that's what we called our p-value. And then depending on the p-value, we get convergence. As long as the p-value is less than 1, it converges absolutely. If this is bigger than 1, it diverges. And remember, if it's equal to 1, we just don't know. So if I want my power series to converge, and the ratio test came out to have the absolute value of x as the p-value, this is going to converge absolutely as long as that p-value, which is the absolute value of x, is less than 1. So we're going to do the same thing that we did in the example in the last video. We're going to squeeze this between -1 and +1. This is now my interval of convergence. This also tells me the radius of convergence has to be 1, since I have to go from starting at 0, since this is a power series centered at 0, I have to go up 1 and then down 1 to get to the endpoint. We do have to test our endpoints though. So the first thing let's do is let's try the endpoint -1 and just see what happens. To test an endpoint, just plug it back into your infinite series. So this is still going to be the infinite series and goes from 0 to infinity. But now I'm going to replace the x up here with a -1. So we're going to have -1 to the n-1 times -1 to the n divided by n. So again, just replacing the x in the power series with the endpoint -1 here. -1 to the n-1 and -1 to the n are always going to be off by a factor of 1. If this one's -1, this one's +1. If this one's +1, this one's -1. So to simplify this series down, this is still going to be an infinite series, but now it's just going to be -1 over n. Remember that this is something that we looked at a long time ago. This was that alternating harmonic series. This converges using the alternating series test. Okay? So we know that that endpoint converges. Let's try the other endpoint, x equals +1. Alright, so again, we're just plugging it in. So we have our infinite series, n goes from 0 to infinity. We still have my -1 to the n-1 out in front. And now I'm going to replace this x with 1, but 1 to the n is still just 1, so we get a 1 over n out in front. Okay, I looked at it a little bit, and I was completely wrong. So this first one is not the alternating series test. This is just the harmonic series factoring a negative sign out to the front. My bad. Fixed it, right? So this actually diverges since it is the harmonic series. It is not the alternating harmonic series because it doesn't change positive, negative, positive, negative. It's just all negative. So it diverges. Whoops. Okay, so when x is -1, it diverges. This one, on the other hand, is the alternating harmonic series because this is going to change -1, positive, -1, positive 1. This is going to be the one that converges since it is alternating harmonic series. So sorry about the mistake. I was going to remake the video, but I'm already like 15 minutes in, and I don't want to re-say all that stuff. All right, we're pretty much done now. So as far as the homeworks go, it's going to ask you a few things. The first thing it's probably going to ask you is the radius of convergence. So for this question, the radius of convergence, remember, is just 1, since we have to go up 1 and down 1 from the center, where my center is 0. It's probably going to ask you for the interval of convergence. So the reason that we tested our endpoints is whether we're going to put less than or equal to or just less than here. Remember that we just saw from our test that when x is -1, it diverges. So I'm just going to have a less than here with -1. But with +1, it converges, which means that I'm going to have a less than or equal to for this endpoint. So this would be my interval of convergence. Other things that the homework questions may ask you is it may ask you, where does this converge absolutely? Remember that the ratio test gives us absolute convergence, but my ratio test only gave me absolute convergence on just the less than. So we have absolute convergence, just -1 less than x less than +1. It'll then ask you, where does it converge conditionally? This is going to converge conditionally only at that endpoint of 1. Remember that it converges conditionally if the alternating series converges, but not the absolute value. So that's what's going on here.